sounds like the ones that we should be working on are 556, 566, and 570. Yes? Okay. All right. So the first thing we're going to have to do with this, we're looking for the weight of the hemisphere, which is 12 inches above. And one of the things that hopefully will make this easier for you, the problem with this picture again is that it's two-dimensional, and you have to think about it being three-dimensional. So think about this jet of water comes up, and think about an umbrella, all right? So it comes up and hits that entire area and then comes back down again. So if you think about that, that's kind of going to make it a little bit easier. So the first thing we're going to want to do is, first of all, what direction are we going to work in? Exactly, why? So let's call, and I think this is how we're going to call this part 1. So we're going to call what goes into the control surface, which is really the hemisphere. We'll call that 2, and then what comes out, we'll call 3, okay? So if we go and we're saying this velocity comes up and it hits this surface like that, what's our, and we're gonna, I guess, work in V. First, let's start with what's our V2 gonna be? Negative or positive? Yeah, so this is gonna be V2. How about our V dot N? Oh, so what I'm calling 2 is right here where it's hitting the surface. So V dot N is going to be negative V2. And since everything else is normal, we'll just go rho A2. All right. And so it enters like this, and then it exits the same way. So what is our V3? We're going to call that V3, how it's exiting. What is that going to be? Negative or positive? That's going to be negative. How about V dot N? Yeah, that's going to be positive. Thank you. So rho A3, and that's going to equal the weight. Now, what they have in the solution, so where is A3? A3 is what's dripping down from the umbrella. And that's, I mean, it's a hemisphere, but it's the whole surface where it's dripping down is that inside of the hemisphere. And that's what makes it kind of difficult, because if you looked at this, you'd say, oh, well, there's a velocity coming down here and there's a velocity coming down here, but it's actually all part of the same velocity that's coming off of the umbrella. What is W? Good question. Weight. So that's what we're looking for, the weight. So remember, if we have forces, normally we would ask what's the force that is needed to do blah, blah, blah. Here, the only force that we have is the weight. So what's the only thing we're given? This height here, and what else are we given? That's it. What happened to V1? Now we're not given V2, at least the way I drew it. So we're given V1, which is equal to 15 feet per second. But one of the things, and it's similar to what we were whenever we talk about submerged surfaces and everything like that, what is it that we are looking for? We're looking for the hemisphere. So what do you think we're going to use that V1 for? That's part of it, absolutely continuity. And what else? Because the problem is, so we don't need V2 and why, or P2, why not? Is there a pressure there? Right, it's open to the atmosphere, so it isn't. So we're doing everything around that hemisphere, and we could use continuity. The problem is we don't know V2, we don't know V3, and we don't know the areas. So what are we going to use V1 in? What's the other tool that, yes, we can do Bernoulli's. So basically what we could say is we'll start at the top. We'll just say V2, all right? So V2 squared is going to be equal to V1 squared minus 2GH. So that's the difference in the height. So since we know, I'm going to pull out my notes because they did not do this very well. Since we know V1, we know 2G, what's our H going to be equal to? 12 inches. Exactly. So from here, we just find that V2 is equal to the square root of V1 squared minus 2G. And now remember, put this in feet, not inches. Okay, so now we have V2. How are we going to find V3? The same way, except again, we're missing areas. So if we tried to do Bernoulli's between V2, V1, and V3, what would we find? Okay, if we tried to do, all right, let's say we want to find V3, and that's equal to V1 squared minus 2G times really the same H. What does that say about, you do know a height difference, and that's where you have to be careful. So it goes up like that, and that's where you start your 2, and then it goes down like that, and that's where you start your V3. So what can we say about that height? V3 equals V2 because those two heights are the same, okay? And that's, as I said, the geometry of this problem is, okay, wait, what? Yeah, we kind of skipped a step. So basically what we're saying is we're going up to here, which is we hit the top, which is the area of that hemisphere, and then we come down from that top, which is V3, right? And basically what we assume, and it's a very good assumption, is that the height is virtually, both of them are 1 foot. Each are 1 foot. Okay, and another way to look at it is to use, as somebody said, the continuity, because the areas are the same. The areas for both of them are that surface of that hemisphere. Okay, so it comes up to the hemisphere and then it goes back down to the hemisphere. So because we know V3, because we can solve for V2, we have this, we have this. What are we missing? We know what rho is. Okay, so how are we gonna find the area? That's exactly right. And so it doesn't matter because the areas have to be the same from continuity, right? So what are we going to use? What area do we know? We know A1, exactly. So we can go V1, A1 equals V2, A2. We've figured out V2. We know A1. We know V1. We can solve for A2, and we put everything back into here, and we can find the weight. And by the way, what sign should the weight have? Yeah. I mean, technically, you should write it like this because it's definitely in the negative direction. And then you'll end up with a positive weight. Okay, so the hard thing about this, and I mean, one of the reasons I chose it was because we hadn't used a weight before. One of the things is to realize that it's a hemisphere and not the disc or something like that, which means that area is going to stay the same for what comes in and what goes out. Or the way you look at it is that they're the same height, therefore V2 has to equal V3. Is that perfect? No, probably that H is a little bit off, but not enough so that we can't calculate it this way. Okay, so does that make sense to everybody? All right. If it only takes us 12 minutes to do each one of these, I'll be able to go to bed early. Well, or maybe not. All right, so we have air discharges from a 2-inch, I lead a very exciting life. Diameter nozzle strikes a curved vein, which is in a vertical plane. What does it mean when it says stagnation tube? Yeah, that means that the velocity equals zero there. It's connected to a U-tube manometer that's located in that. Determine the horizontal component of the force that the air jet exerts on the vane. Neglect the weight of the air, okay? And all friction. So why did they say neglect friction? More than that, Bernoulli, exactly. All right, so let's take a look at what's going on, and let me put some different numbers here. Okay, so what we're looking for is that Rx, the horizontal, and so it's on the vane, which is right here. So what that means is we're going to make our control volume there. And so that means that our control surfaces are there and there. All right, so if we make our control surfaces there, what is our governing equation going to be? And we'll call this 1 going in, and we'll call this 2 coming out. And it's probably pretty obvious that the R sub x is going to be in that direction. All right, so we'll start with V1, okay? What is U1? And get used to this because I'm going to ask you and ask you. And we'll say coming in as V1 and we'll V2. So what is U1 going to be? Positive, okay. How about V dot N? Negative, exactly. So coming in, we have negative rho V1 squared over A1. All right, now let's go what's coming out, and we'll do the V dot N first, because that's the easy one. What is that? That's positive, so that's V2. How about our U2? What's that going to be equal to? Okay, so let me draw this. All right, so this is what's coming out here. And we have to divide it into our different components. So here's X, and here's Y, and here's our 30 degrees. So this is going to be negative, because that U2 is negative, rho V2 squared times the cosine of 30 degrees. And that's going to be R sub x. All right. So what can you say about the relationship between V1 and V2? So the same area. So if it's the same area, what does that mean? So actually, if you look at 1, right, we are concerned with that, and they're equal, right? We are going to use a different pressure later on. But if you think about it, that since we're working in gauge, P1 is going to equal 0 and P2 is going to equal 0. So you said they're equal, yes. So what that means is if the areas are equal, since A1 equals A2, therefore V1 equals V2. And so now we've found that. The problem is we don't have either V1 or V2, even if they're equal. So how are we going to find that? That's always the Bernoulli's and the manometer. That's exactly right. So let's go to the manometer to start with. And I'm going to call that, because it's area 3. And if you notice, it's part of our problem, but it's not part of our equation here because it's not in the control volume, or the control volume, it's not one of the control surfaces. So what we're doing is we're using 3 so that we can find P1 or P2. So how are we going to find P3? We can start here. So we'll say P3. And then when we go down here, right, that's air, so we don't really have to worry about it. And we go there and come up there. So do we add or subtract when we come to the water? Okay, so, and this is where you have to be careful. We're going down here to the air, coming across and then going back up. So when you're going up in pressure, you subtract gamma times our H. And now we're here. What is that pressure going to equal? 0. That's exactly right. So now we can find our P3 is equal to 7/12, so that's in feet, times our gamma. I don't know why I'm writing this out for you. Pound force per feet cubed. So now we have our P3. What are we going to do with our P3 now? So it can't be the same as P1 because P1 is atmospheric. Okay? So we can find P1, and you're absolutely right. We're going to do Bernoulli's at 0.1, and we'll find the velocity. So basically what we're going to be left with is that P3, since there's no change in height, and P1 equals 0, what can you say about V3? So we know that P1 equals 0. What about V3? Yeah, so V3 equals 0 because, as we said earlier, it's a stagnation point. So all we're left with is that P3 is equal to our rho V1 squared over 2. And so now what can we get from that? What is it that we're, yeah. So from this, because we have P3, rho to whatever, from this, we can end up finding V1, and we know that V1 equals V2. And then we put this into this equation, and now we can solve for R sub x. Okay, so when you do these problems, as you can see, a lot of times you use continuity and or Bernoulli's to solve for some of those velocities that we're looking for. So does that make sense? Yep. So what happened to the area term? I left it out. Thank you. That's where it went. Okay, thanks. Any other questions? So we're done for the night? That was a joke. I know you want one. I would want this one. Because I have to have at least one problem that kind of goes a little bit beyond some of the stuff that we've learned in class. Kind of take our knowledge and take it a step further. That's kind of what you do in an exam. All right, so we have a variable mesh screen, linear and axisymmetric velocity profile. So we've seen linear before, but the problem is this is a pipe. So we have airflow through a 2-foot diameter, circular cross-sectional, all right, it's a duct. So we have the static pressures upstream and downstream, and they're different, uniformly distributed over the flow cross-sectional area. And all that means is that the pressure stays the same. Neglecting the force exerted by the duct wall, calculate the screen drag force. And that basically is like an anchoring force, the force that keeps it from moving. So which would be a drag force. So basically, let's take a look at our screen. What's a variable? Let's see what it is. Okay. Oh, they just mean that it is not perfectly even. It doesn't mean, yeah, that's exactly it. Thank you. But the reason they put in things like that is not that you need, they like to give you information about the kinds of things that you would have, but it is certainly not going to change what our answer is going to be. So because we're looking for a drag force, and if you notice a couple of these problems, some of them were find the anchoring force, find the whatever, but we have that one where we had to find the weight, and here we need to find the drag force. But we're doing it the exact same way, where on the left-hand side, we have what's known as the momentum flux, and on the right-hand side, we have the sum of the forces. So what's the real difficulty with this particular problem? What makes this different? The velocity, writing out the equation, all of it. Okay, but the main thing is exactly what you're talking about, the velocity profile. Because we can't just say minus rho v1 squared a1 plus v whatever rho v2 squared a squared, or a1, a2, sorry, because we have a velocity profile. So what we're going to have to do is go back to this. So this is over all the control surfaces are going to be equal to the forces. And the forces, as you can see here, are in the, it's actually in the z direction. So let's actually start with the easy part. What are the sum of the forces? No, and that's where you have to be careful. Because there's a velocity, that this is a momentum equation, we do have forces. And there are a number of things in the problem that tell you that. The first is what we're looking for. We need this drag force. So that's the first thing that we're going to find. Are there other forces that are part of this problem? There's pressure. All right. So this F sub x, I'm going to call it this drag force. Okay. So we have pressure, and we have pressure at 1 and pressure at 2. So let's start with the pressure going in at the into the mesh and then out of the mesh. Okay? So here we have our surface. And so the pressure going into the mesh is on that surface. The pressure from out of the mesh is like that. Because, and there really is some, we can call this way. So what's our pressure force? We'll call this P1, and we're going to call this P2. So our sum of the forces is going to equal, and I will call it F sub x. How about the pressure? Well, let's start with P1. Positive or negative? Okay, so that's plus, and be careful, it's P1, A1. How about P2? Yeah, so that's negative minus P2, A2. So it really helps to draw this surface so you know which way it's going to hit the surface. So that's the sum of the forces. Now let's go to the control surfaces, which is 1 and 2. And we'll start over control surface 1. And so that's going to be rho. Do we know our V1? Yep. Do we know our, sorry, this should have a V dot N in it. So we have our V1, our V dot N dA. I wrote this so poorly. Let me get rid of this. So that's V times V dot N dA. Yes, so P1 and P2 are acting on the mesh screen. They're considered our control surface. Okay, so for this particular surface, control surface 1, do we have to, can we take it out of the integral? Absolutely. We have a uniform velocity. It does not depend on area. And hopefully we know just by looking at it that our U1 is equal to V1. We'll put our rho here. Our V dot N is equal to negative V1. And that's our area 1. Okay. Now we come to control surface 2. And here, our velocity is not uniform. So what that means is we can't take it out of the integral. So the first thing is we have to write a velocity profile. And so what does it say about the profile? The important one. It's linear. So if you remember, when we did it before, remember we said that V equals AX plus B, okay? What's the difference here? What do we have to change? So there's symmetry. What do we have to change in this? Certainly the slope, but something else. Is it in the X direction? What is the no? This is a pipe. This is circular. So instead of X, what do we do? What do we say? Or instead of what it would be is Y. R. That's exactly it. So our U of R, which is what we're looking for, is sum A times R plus B. Yes, sadly, actually cylindrical. So we have two unknowns. We have to have two equations. Take a look at this profile. What can you tell me about it in terms of its radius? And by the way, when we have a pipe, where is our R start from? The center. So this is R equals 0, and this is, and I'm going to leave it like this, R equals R naught. Okay? So tell me what happens to the velocity when R equals 0. What is the velocity exactly? Our U is equal to 0. So 0 equals 0 plus B, therefore B is going to be equal to 0. All right, so now we have that our U of R is equal to AR. So what do we know about the velocity? Where else would we look? And these are what are called boundary conditions, and we're going to be using them over and over again. Okay, so what can you tell me at R equals R0? What can you tell me about the velocity? It's not v1, even though it looks like it could be. It's actually not. It's the maximum velocity, and that's what we're going to say. So you could call it u max, you could just call it u. We don't know it, and we're going to have to find it. So we're going to say that this is our maximum velocity. And so what that ends up being is u max is equal to a times our r0, or r, I should do it this way, shouldn't I? And therefore, a, if you look at this, equals this u max divided by r0. And so now we have our velocity profile, which looks like this. And so now that we have this, what can we do with this? I mean, there are two things we have to do. Yeah, we absolutely have to find u max, and then after we find u max, what are we going to do with that profile? Exactly. We're going to integrate. So how are we going to find u max? We're close. That's very close. It doesn't equal v1, but it is continuity. It's actually mass flow rate, but we can use continuity. So what that means is that our left-hand side, which we know, which is v1a1 equals, and we're going to get rid of the row, is going to be equal to this u sub r dA. Okay, so normally we would say v1a1 equals v2a2, but we can't because that v2 isn't constant. So what we're going to have to do is take this u of r, and what are the boundaries going to be for this integral? 0 to 1. What is 1? Right, 0 to r, 0, and I think you mean 1 like as in 1 foot. So you have to be careful. The diameter is 2 feet, but we're looking at it in terms of r, and that's a really good point because you have to be careful of it. So this is going to be from 0 to 1 foot. So we already have our u of r. How are we going to find our dA? Because that's not in terms of r. What is the area? Okay, so the area is equal to, and what we're looking for the cross-sectional area, that's equal to pi r squared. So our dA dr is equal to 2 pi r, and therefore our dA is equal to 2 pi r dr. So now we can write this as 0 to 1. What's our u r? That's u max over our r0 times r times 2 pi r dr. Okay? So we have our v1, we have our a1. We're going to be able to integrate this from 0 to 1, which takes care of our r. What is that going to pause for a second? Yeah, R0 is 1 foot. Let's try this. Can you see this? Okay. Everybody's happy. All right, so now we basically solved the problem. All right. From this, we get U max. Then we take our U max. Whoops. Let me circle that better. So then we take our U max and put it into here. And then we take this right here and put it into our control surface there. And let me, not there, it's whatever the 2 is, control surface 2. And let me, since we have a little time, let's write that second one out. So basically what it is it's, remember, it's over the control surface, V times V dot N times rho, which I'm taking out, dA. So the first thing is we take that V and we replace it with that U of R. And then you can do signs, you know, negative or positive. Then what do we do with our dA? What's it going to be equal to? Yeah, it's going to be the exact same thing. And I'll tell you, just like we did WDY, when we had dA, this is another thing to know, 2 pi r dr. So we're going to change it to that. We're going to integrate it, and then we're going to be able to solve for this f of x. Okay, so the things to think about here, the main thing is to figure out what that velocity profile. Is there a v squared in the integral? Absolutely. Where did I put it? Yeah, because there's a v here, and then there's this v dot n. So really what it's going to be, if we look at it, is going to be rho, and then it's going to be U max divided by R0 squared, R squared, and then our 2 pi r dr, and the entire thing is going to be integrated over that. And so what you see is once you get this, it's just a matter of taking all the constants out and doing what I hope is a pretty simple integration. So is that making sense now? I mean, the important thing really is to understand that you have to do the integral and you have to figure out the velocity profile. What happens with the R0? Where? There's one right here. Oh, that's here. You can say 0 to 1. Is that what you're talking about? There's an R0 here. What do you mean? What happened to it? Well, yeah, it does turn into a number. What number does it turn into? Exactly. That's the R outside. All right. So the diameter, we could say that the outside diameter is equal to 2 feet. Therefore, the outside radius is equal to 1 foot. Okay? That makes sense? And because you're all here, even though you probably have it, I will give you what the density is, 0.00238 slugs per feet cubed. So you don't have to look. There I go, coming back to those imperial units. So the first problem was in meters. Let's see, the second problem is in feet. Third problem is in miles. Fourth problem is in feet. Hey. But 547, back to meters. Did I do what on purpose? No, you know, I don't look at units. I look at the problem itself. And if I think it's a good problem. The one thing you may have noticed is I take other problems, like for the exam, and rewrite them. And even if they're in feet, I rewrite them in meters. Besides, look at all the knowledge you're getting about imperial units. So those are, yeah, I'm sure that's exactly how you feel. Since we did those three, does anybody have any questions on any of the other problems? No? That's fine. I mean, I'm always happy to call it a night. I'm hoping what that means is that you're understanding this. Okay. Well, then, I am going to, you're welcome, call it a night. I will see everybody tomorrow in class, and we're going to start chapter 6. Yay! See ya. You're more than welcome.